thing I should specify for this question, find the volume of the surface generated when the region in the first quadrant bounded by, so that it's clear, bounded by x squared, y equals x squared, y equals 4, and x equals 0. In part A, rotation is around the y-axis. So y equals x squared, y equals 4. Again, x equals 0 is our y-axis, so that's basically this side right here. It's in the first quadrant, the whole picture. And the rotation is going to be around the y-axis in part A. So we're going to go around the y-axis. Okay. So based on what we just learned previously, our representative rectangle must be perpendicular to the axis of rotation, because remember guys, this is what creates the discs or the washers. When that perpendicular rectangle goes around the axis of rotation, it creates one disc in this case. And you stack them up, you find the total volume. Okay, automatically we know the thickness of this disc is going to be delta y. That tells me which version of the formula I'm going to be using. Is there going to be a hole in the region generated here? When this region goes around the y-axis, is there a hole in the region generated? There is no hole, right? You have a solid, basically your region is completely hinging on that axis of rotation. When that happens, there is no hole in the region. You have a complete solid of revolution. So there's going to be nothing to subtract. The formula we're going to use is r of y squared dy.
So why didn't that other example we did?
Because there was a hole in the region in the other example. Here there is no hole in the region, so there's nothing to subtract. Okay. What is my r of y? Basically, that's the radius of rotation. That's the length of this rectangle here. Normally, that can be represented by a distance x. Again, anytime you find distance to the y-axis, that is x. And what is x equal to for this function? Since y equals x squared, what is x? Square root of y. So that means my r of y is going to be the square root of y. I should also have a pi in the previous formula. Okay, so we have pi times the integral of root y squared. And how about the limits of integration? Where will they come from? 0 to 4, because it should come from the y-axis if you have a dy, right? So 0 to 4. So we should integrate y with respect to y from 0 to 4. So that will give us 8 pi. So once again, if the rotation is around the y-axis, you need a rectangle that is perpendicular to the y-axis. In this case, there was no hole, nothing to subtract. The formula is pi times big R squared. Just be careful, make sure everything is done in terms of the y variable. Okay. Just out of curiosity, what kind of a rectangle, rather a solid, would this generate if you were to rotate it around the y-axis? It would be something like this, a solid with no hole in it, right? That is the three-dimensional solid. Now let's take the same region, but this time go around the x-axis. So part B, take the same region, but now we're going to go around the x-axis. What kind of a rectangle should I select this time? One that is perpendicular to the x-axis. That's going to create a disc or a washer in this case. Is there going to be a hole in this region generated? Yes, because if I just show you the rotation on this picture, yes, there's going to be a hole in the region generated. So we need to go with the washer method here. What is the thickness of our rectangle? Delta x, right? Delta x. And we know this point is 4. Can you also tell me what this point would be if the y limit there is 4? This is the y equals x squared function. What x would correspond to that y? X equals to 2, right? Again, because this is your y equals x squared function. Okay, so volume equals pi times. We know we're going to go with the more general formula, the one that says the big R squared minus little r squared. Our big R in this case is this distance, which is a constant of 4 throughout the region, right? So it's going to be 4 squared. And the inner r is this distance. Actually, that is not a good picture, but let me just draw that one. The delta x is getting in the way, but really little r is this distance from this function down to here. That's my little r. Normally, that distance can be represented by y, right? Depending on what the y coordinate there is, that is that distance. But what is y in terms of x? Because we want everything in terms of x in this case, right? For this function, y is equal to x squared. And what should I be doing with that? Squaring it. If you like, for every question, explicitly state what your big R is and what your little r is. In this case, you want these to be in terms of x because you picked the delta x originally that dictates the variable. In this case, big R is equal to a constant of 4, and little r is equal to your x squared. But when you're putting them into your equation, don't forget to square each one of those. You want big R squared minus little r squared. Now we're ready to simplify and integrate. And how about the limits of integration? Since I have a dx, what should my limits be? 0 to 2. The limits should come from the x-axis, right? So here we have pi times the integral of 16 minus x to the 4, going from 0 to 2, which is pi times 16x minus x to the 5 over 5. That's 32 minus 32 fifths. And I could get common denominators by multiplying this one by 5 over 5. And that will give me 532 minus 132 is 4 times 32 over 5. So I'm getting pi times 128 over 5. In other words, 128 over 5 pi. I know this is one of our early examples, and you're going to do a lot more questions here, but did anybody get it all the way to the end and get it correctly for part B? Anybody who got all the way to the end? Good, I see several students who got it. Fantastic. I know the first one, a lot of students got it. I can also see some students, quite a few also got the second one. Very good. Okay, one more example, and then we're going to do something really interesting. We're going to reinvent the wheel, so to speak. We're going to find the volume of a sphere using this technique. Okay, we're going to come up with a formula for it, which we of course know the formula for a sphere, but can we derive it using this new technique? Before we go to the example, I'll give you one more to work on. Was there a question first? Okay. Okay, I don't want that one. Okay, this is the one I want. Okay. Find the volume of the surface generated when the region bounded by y equals x y equals x squared Yeah, I think I have too many things going on there. I should delete my x equals 0 there. So just find the region, find the volume when the region bounded by y equals x and y equals x squared in the first quadrant is rotated around the x-axis. Okay, I want to give you some time to try to set it up. Once again, you decide what kind of a rectangle would be good to choose here. So we're going around the x-axis. We start by picking our representative rectangle perpendicular to the x-axis. That's going to create the washers in this case. The thickness here is delta x. Thickness is delta x. Okay. Is there going to be a hole in the region generated? Can you see what's happening here? When that two-dimensional region goes around the x-axis, you get a three-dimensional solid that has a hole in the region. Roughly speaking, your region, that's not going to look very well, but something like this. There's definitely a hole in this region generated. So we're going to go with the big R squared minus little r squared formula. And by selecting our rectangle the way we did, we already know everything should be in terms of x. Okay, big R is your distance from the axis of rotation to the outer part of the region. So for this example, your big R is your function x, and little r is from your axis of rotation to the inner part of that rectangle. So that is, for this example, x squared, right? So now we're going to put them into the formula, and as you do that, don't forget to square them. So big R squared is going to be just x squared. And what should I have for little r squared here? X to the fourth, right? Because it's x squared squared, so that'll be x to the fourth. And the limits are from the x-axis again. You can set the functions equal. If you do that, you're going to end up getting x equals 0 and 1, two solutions. So those are the limits of integration. Now integrate each one and plug in the limits. And I believe that turns out to be 2 pi over 15. Okay, that finally brings us to our last example, which is the one I promised a little earlier. Find the volume of a sphere. By the way, what is the volume of a sphere? If the radius is r, does anybody remember? 4/3 pi r cubed. It's a known formula. I don't ask you to memorize that formula. We can always locate it. But here the question will be to derive the formula that we've taken for granted for so many years. Derive a formula for the volume of a sphere. In other words, show that volume of a sphere is 4/3 pi r cubed. I believe it was Archimedes who first came up with this, and it was like BC, maybe 500 BC. Somehow, with the little that he had, with the mathematical knowledge, he was able to come up with a volume for the sphere. Now we're going to see if the techniques of calculus are really consistent with what we currently know. To generate a sphere, what kind of a region do you think you should be rotating? A circle, right? Because like if you have a line and you rotate a line, this is your group activity problem, you end up with a cone. If you have a circle, say a quarter of a circle even, you rotate it around the x-axis, then you can end up with a, say, a hemisphere, which you can then multiply by 2. So let's begin with a quarter of a circle with radius r. And we're going to rotate this around the x-axis. Does anybody remember the equation of a circle formula? What was the equation of a circle?
Oh, on a graph?
Good, Chris remembers it. X squared plus y squared, and that's it, equals r squared. Does everybody remember this formula? We haven't used it in a long time, equation of a circle, right? But I need to know this function, like what is y equals f of x for this function? So if I was to solve for y in this equation, first I would get that y squared is equal to r squared minus x squared. And what is y? Technically it's plus or minus, but because we're in the upper part of the y-axis, we can just take the positive one and get away with that, because again, we're only dealing with the positive portion of that curve. So positive square root of r squared minus x squared is what we need. Okay. Now, we're going to rotate this circle around the x-axis. That's going to give us a hemisphere. Later, we can multiply the answer by 2, and we'll be done. The important thing to remember here is that r is just a constant. Okay? So when we're integrating, if you're integrating r, it's going to be like r times x, because r is like 5. An integral of 5 is 5 times x, right? So r is just a constant. Okay, what kind of a rectangle should I select if I'm going around the x-axis? What kind of a rectangle would you select from the region? A vertical one. In other words, one that is perpendicular to the axis of rotation, something like this. What is the thickness of that? What is the thickness of this rectangle? Delta x. Is there going to be a hole in this region? No holes. There's nothing to subtract, right? So our formula in very rough format is going to look like this. Pi times big R squared dx. Correct. Okay. Now, what is my R of x in this case? What is this distance? Whatever the function is, right? That is your R of x. So the function happens to be the square root of r squared minus x squared. But what should I do to that? Square it. How about the limits of integration? 0 to r, right? Because we're starting at 0, going all the way to r on the x-axis. Okay, let's square that quantity, see if we can simplify it a little bit. So this is pi times the integral of, well, we just lose the square root, right, when you square it. Okay, here's the interesting part. Remember, r squared is a constant. We don't know what the radius is, but no matter what it is, it's a fixed number. So think of r squared as 25. What is the integral of 25 with respect to x variable? 25x. So what is the integral of r squared with respect to the x variable? R squared x. So that's the first part. What is the integral of x squared with respect to x? Right. Nothing unusual about that one. That's old stuff, right? X cubed over 3. The limits are from 0 to r. And remember, this is x equals 0 to x equals r. Start plugging in the upper limit. For everywhere you see an x, plug in an r. Then plug in a 0 everywhere you see an x, and simplify. We have pi times r cubed minus r cubed over 3. How do you simplify that? R cubed minus r cubed over 3. Or get common denominators if you like. Either way would work. So you have 3r cubed minus r cubed. So you're going to be left with pi times 2r cubed over 3. In other words, 2 pi r cubed over 3. Now, we didn't get that formula we're looking for. What went wrong? This is exactly, we got to double it. So volume of a full sphere will be pretty amazing, huh? 4 pi r cubed over 3, a formula we've always taken for granted. You have to study so much mathematics in a sense to be able to prove it. But again, this is not the only way to prove the volume of a sphere. There are some geometric techniques that use geometry, which I'm sure Archimedes relied on like 500 BC or so. So he did not have techniques of calculus to prove it. But this just confirms our